I'm going to demonstrate getting started on the first project for CS2810. This assumes you already have CodeGrinder set up. If you don't, there are separate videos to help you with that. It shouldn't matter which platform you're working on. I'm going to be demonstrating from a Mac, mainly because that's the easiest place to do a screencast. But the process should be basically the same for any of the major systems. Which text editor you use is up to you. I'm going to demonstrate using Vim just because that's my editor of choice, but it shouldn't matter. You should be able to use any editor you wish. I'm going to type grind list, and this will show me all the assignments that I have available to me. If you can't find the one you're looking for, it probably means you need to go into Canvas and click on that assignment and click on the button that says load the assignment in a separate window. And that registers the assignment with CodeGrinder. You have to do that once for each assignment. I want number 3, the one that for me is listed as 3. Your numbers will be different. It's an assignment number. But I want the one that says Maze Directions Project under CS2810. And when I do that, that creates a directory. In the directory that I was at, I did this in my home directory. It creates a directory called CS2810. And if we do multiple projects from CS2810, they will all go under that same subdirectory. And then it creates a directory inside there where the specific assignment is. So I'm going to change over into that directory. You can see it told me which files it was writing, but I'm just going to do an ls here even so. There are a few different files. Directions.s is the starter code. That's where I'm going to start working. The make file is to help me build it locally. Not too helpful in this case since I'm not running on an ARM machine, so I can't actually build and run the assignments locally. I have to do it through CodeGrinder, or I could connect to Orpington and do this entire process there if I wanted to run things locally. The tests directory contains the unit tests, and we're going to ignore that for now. The _doc directory contains the documentation. There's a file called index.md in there that you can read the problem directions. So I'm going to load directions.s into my editor. I already know the directions, so I'm not going to go and open that file. Or actually, maybe I will split it. I'll load it just so we can refer to it. So our goal with this project is to write something very similar to Hello World. We're going to write the word left to the screen. That will be the first of 3 steps in this project. And here's my starter file. It has just a skeleton outline of what we'll be doing. It says global directions. It's because we're being asked to write a function called directions that, again, for now just prints the word left to the screen. It gives me a place to starts the text segment, and it has this directive to the assembler, .func directions. That tells it that I'm going to create a function. It doesn't affect how the code works, but it's a good idea. It helps with the debugger, so the debugger kind of knows where your function boundaries are, and that ends with this .endfunc. We have the label directions, so this is where I'm going to start writing my code. For now, it doesn't take any parameters, but it does need to, it's going to need to make use of R7, the R7 register, because it's going to be doing a system call. And so the first thing I'm going to do is save R7. So I'm going to push R7 onto the stack, and I'm going to go ahead and push the link register as well. You should always push an even number of registers onto the stack. That's just part of the ABI for ARM processors on Linux. The stack pointer should always be a multiple of 8. So if we're only pushing 4 bytes, R7 is the only thing we really need to push right here. We'll go ahead and add something else to just pad it out to a multiple of 8, or 64-bit boundary if you prefer. Once I've done that, the next thing I need to do is prepare a write system call. And the directions have this. I've got some awkward line wrapping here. But I want to do it call a system call as though it was this C function call. It's called write. It expects a file descriptor as its first parameter, a pointer to memory that contains the data it's supposed to write, and the number of bytes that it's supposed to write. So I'm going to go ahead and define a couple constants to help out here, and you can get these from the text of the assignment. Syswrite is system call number 4. Standard out is the file descriptor we're going to write, and it has the number 1, but I think standard out is a much nicer name. And that should be enough to get us started. So I'm going to prepare that system call. And that means I need to load the parameters to the system call into R0, R1, and R2. So I'll use the LDR instruction to load a value into the register. I'm going to load into R0 standard out. So that's just loading the constant value 1 into standard out. Into R0. Into R1, I'm going to load the address of the message I want to print. Now that doesn't exist yet. So I'm going to say equal left, and I'm going to go and create that. I'm going to switch over into the data segment, since I'm putting data and not code. And I'm going to create a label called left, and I'm going to store some ASCII text at the location pointed to by that label, the message left with a new line at the end. And I'm going to also record the length of that message as a word in memory. And what that means is it's going to store a 32-bit value, and I'm saying that the 32-bit value it should store in memory is the dot means the current memory location minus the memory location of the left label. So that should be the number of bytes that were recorded by this ASCII directive up here. It stored an L, E, F, T, and a new line, that's 5 characters. So if I take the current location minus left, that will be the value 5. It's going to store that value in memory, and len is going to be the address where in memory we can find that number 5. So length is not the number 5, it's the address of where we can find the number 5. Likewise, left is not the left label is not a string, it's not left new line, it is an address in memory where we can go and find the string left new line. So back up here to our function to print it, LDR, we loaded R1 with the address of where left is stored. We're going to load R2 with the address of where length is stored, but we don't want the address, we want the actual number 5. So I'm going to do a second instruction to load into R2, and that's square brackets. It's not rendering properly. There we go. Those are square brackets, and anything inside square brackets is a memory location, and this is telling the instruction to go fetch that value from memory and store it in R2. So we first loaded the address where it could find the number 5, and then we went and said it go fetch the value from memory at that address and load it into R2. So R2 will now contain the number 5. Then to finish preparing the system call, we load the system call number into R7. And R7 is just where that always goes. So I'm going to load the number of the right system call. And then I'm going to do a service instruction and run service number 0. That's what invokes the operating system and asks it to process the system call. So that should write the word left and a new line to the screen. Next, I'm going to examine the result of that. So I'm going to test R0 against itself. The result of the system call comes back in R0, just like the result of a function comes back in R0. If that was less than 0, that indicates there was an error. So I'm going to say branch if that was greater or equal to 0. I normally branch when it's successful and then immediately handle the error. So I'm going to say if it was okay, if the result was greater or equal to 0, then I want to have it go down to label 1, which is going to be a forward reference. I haven't created it yet, but I will in a moment. Now this is where I'm going to handle the error. If there was an error, what I want to do is load a value into my R0 register that indicates there was an error. And I'm going to just create a constant for that and say there was an error when a write happened. I'll come back up here and define another constant for that. So I'm going to have error write just be error number 1. And I'm just making that number up. It's just something that's non-zero. And then I'm going to quit. So I'm going to pop R7 and the program counter off the stack. So that's going to restore the value of R7 that I pushed earlier. The link register, the other one that I pushed, is the address where execution should resume after the directions function runs. And so instead of popping that back into the link register, I pop it into the PC register, which is where the address of the next instruction to run goes. And so that will immediately return from the directions function with my error status code in R0. So in one step, it restores R7 to its value, as we always must do, and it returns from the function. So now I'm going to put the label 1, which was my branch target. This is if everything succeeded. If things succeeded, I'm going to load the number 0 into R0 to indicate success, and then I'm going to do that same pop instruction. Pop R7 and PC into the register. Or excuse me, pop those off the stack, which has the side effect of exiting from the function. So that's the end of my function. Now to test this, I could go right away and say grind grade, but I first want to actually test it by itself. And so to do that, I'm going to create a start label, and these are the let's see, I'm also going to, since I'm going to be doing an exit system call, I'm going to create a constant for that. But now under start, I'm just going to do BL directions. BL is branch with link, so that means go down to directions, but also put that value in the link register that tells it where to come back when it's finished. When it does come back, it already has a result in R0. That's where function calls put their result, and that's also where the first parameter to the system call is, and I'm going to prepare a system call for exit, the exit system call. So I'm going to load the exit code, the exit system call number, which happens to be 1, into R7, and then I'm going to invoke that system call. So start is where my program will begin running when it's a standalone program. I'm going to tell it call directions and then return whatever it returned, hand that off to the system, to the exit system call, and exit. Now one last step, I need to export the underscore start label so that the linker can find it and the operating system can find it to run it. So now I'm going to build it by saying grind action run. That uploads it to the server. Whoops. What did I do? Underscore start. Underscore start. LD cannot find the entry symbol underscore start. It's right there. Grind action run. What did I do before? I thought I just typed the exact same thing. I think I forgot to save. Yeah, it's important to save. Okay, so it assembled it, and here it's showing you the exact commands you would type with a $sign in front of each one. So it assembled it, it linked it, it ran the code, and we can see it printed left and a new line after it. So now that I believe that it works, I'm going to submit it for grading. Now the grading script is going to run it against unit tests, and it has its own entry point, its own underscore start entry point. So I'm just going to delete that as a global declaration. I can leave the code there, that's fine. It won't find it now because it will be a private label, so that'll just be some dead code. So I'm just going to make that little change, and now I'm going to say grind grade, which submits the code for grading. So it runs everything quietly. If it succeeds, all it'll do is say at the end that it succeeded. If it fails, it'll give me a report and let me do more. So I can go back, give me some hints so I can go back and correct it. But this succeeded. Step 1 passed, moving to step 2. So it deletes the directions for step 1, deletes the test file, creates the directions for step 2, and the test file for step 2. But that means I've successfully finished step 1. Now, as you do this step, I encourage you to not blindly copy and paste. Try to understand what you're doing. Go to read through it carefully, and then go through and do as many steps as you can on your own. Then come back, watch the next segment, and go do those on your own. You'll learn it much better that way than if you just blindly and copy paste and paste things into your editor. So I hope that is helpful.